Hey everyone, welcome back to Calculus 2. This will be lecture 5 of the course, and in this section we're going to discuss integration by substitution. And so this is where we'll get into the idea of a U substitution being used to integrate a function. So this section is this is an extremely important integration technique, possibly the most used integration technique, maybe second only to integration by parts. This technique is going to be really comparable to the chain rule technique that we had with differentiation. So let's go ahead and jump right into it. Okay, so we'll call this section 1.5, integration by substitution. Okay, so recall, previously we've talked about having y equal a function of u and u equaling g of x. Given this, the derivative ddx of f of g of x is equal to f prime of g of x times g prime of x. Okay, so this is the chain rule from Calculus 1. So then the antiderivative definition implies that the integral of f prime of g of x times g prime of x dx should be equal to f of g of x plus c, which would be f of u plus c, right? So this is basically like, so the derivative goes, starts with this and gets you here, and then from the fundamental theorem of calculus, we know that we can integrate this and get back to the original, right? That's the interchange, the inverse nature of these two operations, integration and differentiation. So let's take this as kind of the starting point for integration by substitution, and let's look a little bit closer. Okay, so let's get the theorem out here and see what's going on. So let g be a function whose range is an interval I. Okay. Let f be a function that is continuous on I Okay. If g is differentiable, on its domain, and f is an antiderivative, big F is an antiderivative of little f on I, then the integral of f of g of x times g prime of x dx is equal to big F of g of x plus c. Okay, so you could also say if u equals g of x, then du equals g prime x dx, and the integral of f of u du is equal to f of u plus c. Okay, so kind of two ways to think about it. So this is sort of the explicit kind of like chain rule way of thinking about it, which is fine. we'll start with that, and then this is sort of a explicit substitution kind of way of thinking about it. They're equivalent, right? But we'll look into it in a second here. So the key here, well, one of the keys, possibly the key, is to get serious about pattern recognition. So pattern recognition is really important with these use substitutions. Okay, pattern recognition is important. So let's do an example here. So if I have the integral of 2x times x squared plus 1 to the 4th power dx, this is going to fit the pattern This fits the pattern of the integral of f of g of x, g prime of x dx. Okay, so namely, we would say f of g of x is equal to x squared plus 1. That's the x squared plus 1 to the 4th power part. Right, so then obviously the g of x here is the x squared plus 1. And the g prime of x is the 2x out front, right? Okay, so you got f of a function, f evaluated g of x, that whole thing, that composite function, times g prime of x. And so you can see all those pieces here. You got the f of g of x, the g of x naturally is inside the f of x, and the g prime of x is 2x. So here's your 2x, here's your f prime of g of x, or sorry, your f of g of x, and then this piece inside your g of x. Right, so this may seem like a lot of craziness, but we'll do some more examples, and hopefully the patterns will start to emerge. Here's another example of this pattern. Right, so what about the integral of 3x squared times the square root of x cubed plus 1 dx, right? So that whole deal. Well, the f of g of x in this case is the x cubed plus 1 square root. So that means the g of x is what's inside there, the x cubed plus 1. And so then naturally the rest of it outside here you can see is the 3x squared, which is the derivative of g. Okay, so let's write this really explicitly. So you could reverse this and kind of write it like this instead. Right, so this is the f of g of x part. This is the g prime of x part. And then so you can see naturally that this piece here inside, that's the g of x part. And so you can kind of see all the parts there. And that's probably the most important thing about this kind of problem, this method, right? Is just being able to spot this pattern when it's present. So another example, this one's slightly less obvious, I think. Secant squared x times tangent of x plus 3. So you got kind of these two pieces. So here you've got a f of g of x in this tangent of x plus 3 part. And so that means you've got a g of x function here, which is just the tan x part, and a g prime of x piece in the front here, right? So when you differentiate tangent, you get secant squared. Okay, so this one's a little slightly less obvious, I think. Okay, so these are all examples where the pattern is explicitly in the integrand. You explicitly have f of g of x, g prime of x in the integrand. Now, very often, in fact, maybe most of the time even, you will have an integrand that almost fits this pattern, but not quite. And so it may be possible to change the integrand in some way so that it does fit this pattern, right? So consider an example here. Like, so if I have the integral of x times x squared plus 1 to the 4th power, right? So here this is like an example that we just looked at, but if I have f of g of x equals x squared plus 1 to the 4th power, then that means g of x would be x squared plus 1, and g prime of x would be 2x. Now, we almost have that, right? We certainly have the f of g of x and the g of x part. It's just our g prime is a little different, right? We only have x, we don't have 2x, right? So the pattern isn't quite there. But this is an example where we can easily convert this into a form that does fit this pattern, right? So namely, we can write the integral of x times quantity x squared plus 1 to the 4th power. That can be rewritten as 2 over 2 times the integral of x squared plus 1 to the 4th power, which of course can be written as 1/2 times the integral of 2x times x squared plus 1 to the 4th power. Right, so basically we've added the 2 in where we need it, but we just have to, sort of compensate by, dividing the whole integral by 1/2 at the end. Right, and then so in this way, we can see that here we have the pattern, right? We have our f of g of x equals x squared plus 1 to the 4th power. Our g of x is x squared plus 1, and our g prime of x is 2x. So we have all of the pieces. You can fit this pattern together and quickly calculate this integral. Okay, good. So these are just examples of spotting the pattern. Now let's go ahead and do some examples where we actually use this technique to identify an indefinite integral. So let's evaluate the integral of x squared plus 1. So I guess this is what we just talked about. Yeah, let's do the 2nd power, just make it different, times 2x dx. Okay, so here we would right, so just basically the key to doing these integrals is to just kind of recognize a pattern, maybe make a note of the pattern just while you're doing it. So f of g of x equals x squared plus 1 squared. That means g of x is x squared plus 1, and g prime of x is 2x. Okay. Okay, so then what we need to do, right, so we've got our integral. Now, what did the theorem say? Right, well, the theorem said then that this should be equal to f of g of x plus c. Okay, so what is our f of g of x? Well, that's just going to be the antiderivative of the f function, right? And so in this case, it would be equal to 1/3 x squared plus 1 to the 3rd power plus c. Right, so we would integrate the f part of this, which would be like this thing here. Right, so this would be like kind of that power rule. Right, it would be, you'd raise the exponent, you'd raise this piece of it to the 2 plus 1 power and divide by 2 plus 1. Right, so that's all we've done. And so the integral is really easy to find using this technique. How about another example? Evaluate the integral of 5e to the 5x dx. So in this case, the gx g of x is equal to 5x. Okay, that means g prime of x is 5, right? And so we have that pattern. So the f of g of x, well, I guess I should put that in there too. The f of g of x is e to the 5x, right? So we have that, e to the 5x, and we've got the g prime of x out front, actually the 5. So this fits the pattern perfectly. So the integral of 5 e to the 5x dx should be equal to, well, it's going to be equal to f of g of x plus c. Now, what is the antiderivative of f? Well, it's just e itself, isn't it? So this would be, again, equal to e to the 5x plus c. Okay. So this is amazingly convenient, right? So basically just taking the idea of the chain rule and basically reversing it on itself. Okay, now sometimes you can just kind of do this sort of plug and chug approach to this and you'll be fine, but I think what most people tend to do is they tend to gravitate towards a formal change of variables. Okay, so a formal change of variables, and it's basically going to be based on this integration by substitution idea, this theorem that we just looked at. But what we want to do with the formal change of variables is we want to completely rewrite the integral in terms of u and du. Okay, so this is usually advantageous because it just helps you to keep everything straight. It helps keep sort of the patterns kind of sort of fall out of the change variables, and it makes it harder to kind of miss something, right? As well as the fact that there are like niceties that can come along with the change of variables, which we'll get into in a moment. Let's talk this method through a little bit closer. Let's talk this through. What is this all about? So letting u equal g of x, right? Then du, the derivative of u, is equal to g prime of x dx. So we have the integral of f of g of x g prime of x dx is equal to the integral of f of u du, which is equal to f of u plus c. Okay, so this is sort of the formal setup, but let's so you can kind of see that this part here is captured by this du, right? So that's this piece here becomes that, and then f of g of x is just f of u. All right, so that's sort of notationally how this change of variables works out. Let's do some examples, and I think the method will become pretty clear after a couple of examples. So let's evaluate the integral of 2x minus 1 square root dx. We're going to use change of variables on this explicitly. So we'll set u equal to 2x minus 1. Okay. So then du is equal to 2 dx, right? Just differentiating this, we get 2 times dx. Okay. So what that means then is that if I have the square root of 2x minus 1 dx, then what I have is the what I have is the integral of the square root of u, and then I still have this dx, and I can't substitute 2 dx in for dx, so what I can do is I can take this little equation here and see that du over 2 is equal to dx. So the dx part of it, I just plug in du over 2. Okay, and this can look a little cumbersome at first, but I think, after you mess with it a few times, you kind of recognize, okay, this is really just 1/2 times du. So let me write that explicitly. So this is the square root of u times 1/2 times du. Okay, and then what you obviously would want to do here is write this as 1/2 times the integral of the square root of u du. Okay, so important to notice here, all I've done is I started with this function here, this integral here with this integrand, and instead of the square root of 2x minus 1, I plug in the square root of u, right? And that's just because I've chosen 2x minus 1 as my g of x, and so u equals 2x minus 1. U equaling 2x minus 1 implies that du, the derivative of u, is equal to 2 times dx. Okay, and that's also going to imply that dx itself is equal to du over 2. Okay, so I just make those substitutions. I substitute here with this, and then I substitute this guy with that thing over there. When I do all of that, I get this right here. Okay, and then I can integrate this as just, you can think of it as 1/2 times u to the 1/2. Okay, and then that is just what? It's 1/2, and then it's u to the 3/2 divided by 3/2 plus c, which is 1/2 times 2/3 u to the 3/2, which is 1/3 u to the 3/2. Okay, and then what's u? At the end, of course, you want to ditch the u variable. Sorry, these are all plus c, got to hang on to that. At the end, you want to ditch the the u variable and go back to your original variable using this up here. So this would be 1/3 2x minus 1 to the 3/2 power plus whatever your constant of integration happens to be. Okay, so I know that seems like, what in the world? But it's all really quite simple, actually. You pick a u, right, and the u should correspond to basically the g of x from the previous method, from the chain rule, right? So it's going to be the inner part of the integrand usually. So u equals 2x minus 1. From that, you differentiate, and you get du equals whatever u prime is, in this case 2, times dx. If necessary, you solve for dx, right? Sometimes it's necessary, sometimes it isn't. And then plug everything in, integrate with respect to u, and then convert everything back to x's. Okay, let's do another example. Let's evaluate the integral of x times the square root of 2x minus 1 dx. Okay, so here we want to let u equal 2x minus 1. So then du is equal to 2 dx. Okay. All right. So we can say that du over 2 is equal to dx. So usually what's a good idea to do is to kind of look at what you've got so far and see, can you substitute everything fully, right? So you can definitely get this part here can be written as u, this part here can be written as du over 2, but I'm still stuck with this x in the front. So one of the things that will commonly happen is that you will have some sort of straggler piece here. So what you can do is you can just use this to rewrite in terms of u. So u equaling 2x minus 1 is going to imply that 2x equals u plus 1, which is going to imply that x itself, this little x here, should be written as u plus 1 over 2. Okay, so I know this seems like a lot, but now we have all the pieces. We've got this piece here for that, we've got this piece here for the dx, and then x can be written like this. And so what happens when we do all of this? Well, we get the following. The integral of x times the square root of 2x minus 1 dx can be written as the integral of u plus 1 over 2 times the square root of u times du over 2. Okay, and then obviously you're going to want to clean this up as much as possible, and when you do that, the 2's can be multiplied together and you get 1/4 on the outside, and then you have u plus 1 times, and I'm going to write this as u to the 1/2 du. That's a du. Well, it looks a little bit like a w, but it's supposed to be du. And then, of course, you can rewrite that as 1/4 times the integral of u to the 3/2 plus u to the 1/2 du. And kind of switching pages here, that can be integrated really easily, right? 1/4, and then u to the 3/2 would become u to the 5/2 over 5/2 plus u to the 3/2 over 3/2 plus c, and you get, let's rewrite everything, 1/4, and then it's 2/5 u to the 5/2 plus 2/3 u to the 3/2 plus c. Okay, and most of this stuff there's a lot of canceling that can happen. The 2's can cancel with the 4. So I guess we could write it as 1/2 u to the 5/2 over 5 plus u to the 3/2 over 3. And so you would get u to the 5/2 over 10 plus u to the 3/2 over 6 plus c. And then you don't want to stick with u. At the end of the day, you want to get rid of the u's and plug back in whatever u was. In this case, u is equal to 2x minus 1. So this would be 2x minus 1 to the 5/2 power over 10 plus 2x minus 1 to the 3/2 power over 6. There we go. So that's the integral. So when you when you evaluate this integral, this is the form of the family of antiderivatives for this guy. Okay. So again, this is one of those techniques that are can seem very tricky at the onset, but after you do 2 or 3 of these, maybe 3 or 4 even, maybe 4 or 5, you really it becomes like second nature. It becomes, I think, if you remember learning the chain rule, it probably seemed extremely cumbersome initially, but after you do it a few times, you realize that it's actually fairly intuitive. And that's the same thing with this U substitution integration technique. Let's do another example. Let's evaluate this guy. Sine squared of 3x times the cosine of 3x. Okay. So here we're going to use the change of variable, the U substitution technique. So let's let u equal sine of 3x. Now notice this is sine of 3x squared, right? Sine squared of 3x. So this is like the inside function of a u squared. Okay, so then du is equal to the derivative of sine of 3x. Now you got to use the chain rule on this, and so you would get cosine of 3x times 3. So I'm just going to write it as 3 cos 3x dx. Okay, and so that means then that du over 3 is equal to cos 3x dx. Right, so just kind of looking up here, you see, okay, I've got this piece taken care of with this u, so this will just be u squared, and then this whole thing here is going to be du over 3. Okay, so the whole thing is I can substitute something in for the whole expression, the entire integral, and what I get then is u squared times du over 3, which is obviously very easy to integrate. 1/3 times the integral of u squared du. So that's 1/3 times u cubed over 3. So I get 1/9 u cubed. And then my u I just toss my u back in and we're good. So this would be 1/9, and then the u is sine of 3x. And so now it's cubed. Okay, so probably better written as 1/9 sine cubed 3x plus c. Okay. Now, just like we've seen in the past, any of these integrals that we evaluate, we can confirm the accuracy of the thing by differentiating, right? So if I wanted to check this, I could differentiate this and I would expect to get back this integral, right? So let's do that in this case. Let's differentiate 1/9 sine cubed 3x plus c. So when I differentiate this, let's pull the 1/9 out. And let's write it as sine of 3x cubed. And then I'm going to drop the c because I know that the derivative there is 0. We'll just put plus 0. Okay, just to make it clear what happened to that. So this is the chain rule inside the chain rule inside the chain rule, right? So you got 1/9 on the outside, and then I got to differentiate the, so when I do this, what I end up with is 3 times sine squared of 3x. Okay, differentiate the sine of 3x, and I get cosine of 3x times 3. Okay, now does this all sort of sort out? Yeah, the 3 and 3 are 9, so the 1/9 disappears, and I just have sine squared 3x times cos of 3x, right, which is exactly what we started with. Perfect. Okay, so you should be able to differentiate anything that you integrate and get back to the original problem. Okay, so done a bunch of examples. Let's talk through. Let's kind of offer up some guidelines for change of variables. So guidelines are nice, right? So this can be a little bit tricky. So when you're doing a change of variable integration, what you want to start with is by choosing a u. So choose a u equals g of x. And this is usually the inner part. Okay, the inner part of whatever the function happens to be that you're integrating. Okay, then you want to, once you have that u, you want to calculate du, which is just basically g prime of x dx, right? So whatever g happens to be, differentiate it. And then once you've done that, you want to rewrite the integral in terms of u and du. I guess and du. I mean, I'll say that, but really that should be kind of self-explanatory. Okay, so you want to rewrite the integral in terms of u, and then you want to integrate. Okay, integrate. The integrals in terms of u, so integrate across those u variables, and then obviously replace u with g of x in the end. Okay, so that's the idea. And then, of course, if it's easy, you might as well verify your integration by differentiating the result. I guess I'll put that in there. Verify by differentiating the result. Right? That's kind of like your elementary school teacher telling you to, you can always check multiplication by division or vice versa, or addition by subtraction. It's basically the same idea, right? So it makes sense to do that, especially if the derivative is easy to calculate. If it isn't, then maybe you can hold off. But so these are the guidelines, kind of the steps that you would want to take for calculating using this technique with integration. Okay, all right. So let's talk about. Let's get a theorem out here. So this theorem is called the general power rule for integration, and we've certainly seen this already, but let's bring it out, and we're going to recast it a little bit in terms of these u substitutions. So this is the general power rule for integration. Okay, if g is differentiable, then the integral of g of x to the nth power times g prime of x dx is equal to g to the x n plus 1 over n plus 1 plus c. Okay, of course here n is not equal to negative 1. All right, now kind of this is more general because previously we had been saying something like we said the integral of x to the n dx is x to the n plus 1 over n plus 1. Well, here we're saying x, it doesn't have to just be x. Now it can be a function all its own. So another way to say it, using the u substitution language, is to say that the integral of u to the n du is equal to u to the n plus 1 over n plus 1 plus c, where u is equal to g of x. Okay. All right, so this is basically kind of what we just discussed, right? But specifically, when you've got an exponent here, right, then the pattern becomes very obvious, and it's super convenient to think of it in these terms. So let's do some examples of just seeing this pattern in the integral. So if I have 3 times 3x minus 1 to the 4th power dx, right, then I can write that, I can change the order there, 3x minus 1 to the 4th times 3 dx. Right now here, this part here, this is my u to the 4th, and this would be my du. Right, if I differentiate 3x minus 1, I just get 3, right? 3 dx, right? So that's that part. So I would just say I could straight integrate this really quickly by just saying, okay, it's 3x minus 1 to the 5th power over 5 plus c, right? So then this piece here would be u to the 5th over 5. Okay. Right, so this is using the u substitutions, you would naturally arrive at this answer, but in some cases you can just see it if you get this pattern built into your thinking. So another example, e to the x plus 1 times e to the x plus x dx. Right, so again I could switch the order of this, e to the x plus x times e to the x plus 1 dx. Right, now this you can think of as your u to the first power, and that makes all of this the du. Okay, now notice if this is u, that's u to the first power, not u prime. If this is u, then when I differentiate this, I get e to the x plus 1, which is this part. So if this is u equals e to the x plus x, then du is equal to e to the x plus 1 dx. Right, and so this whole thing can be quickly evaluated as e to the x plus x squared over 2. Right, so then this would just be u squared over 2. Right, if I have a u to the first, then the integral would give me u squared over 2. So hopefully the pattern is beginning to emerge here. Another example, how about the square root of, excuse me, the square root of x cubed minus 2 times 3x squared dx. Okay, so something like this. So this here would be like u to the 1/2. So then the derivative of x, if u is x cubed minus 2, then the derivative of that is 3x squared dx, and so this would be your du part. And so then the integral here would just be whatever u is, x cubed minus 2, raised to, instead of 1/2, it'd be 1 more than that, so it'd be 3/2 over 3/2 plus c, and so this would be u to the 3/2 over 3/2. All right, so that's another example of kind of seeing this pattern. Let's do one more where we're just kind of focused on the pattern here. What if I have something like this, negative 4x divided by 1 minus 2x squared all squared? Something like that. Well, let's rewrite it first, and let's write it like this. 1 minus 2x squared squared times negative 4x dx. Now, this part here, this is u to the, oh, that should be negative 2, sorry, because it came to the top, right? So the exponent becomes negative 2. This should be u to the negative 2 power. And so when I differentiate 1 minus 2x squared, I definitely get negative 4x. And so that means this whole thing here is the du. So the answer then, the integral would evaluate to 1 minus 2x squared to the what? Negative 1 power divided by negative 1 plus c. And so this would be u to the negative 1 over negative 1. Okay. All right. Okay, very good. So we'll do more examples of this, and this will be kind of a staple going forward, this kind of integration. But what happens, what can we say about, what happens if we try to use this technique with definite integrals? So that's the subject of this next theorem. So if the function u equals g of x has a continuous derivative on the interval a to b, and f is continuous on the range of g, then, so now we're talking a definite integral from a to b of f of g of x, g prime of x dx, right? So this is the same integral that we talked about before, except now it's a definite integral. Then it's going to be equal to the integral of f of u du, where we evaluate the limits of integration inside the g function. So this is a little weird at first, but what this basically shows you is that you can directly evaluate the u function in a definite integral, right? You can do it directly, but only after. But obviously, in order to do that, you have to adjust the limits of integration. Okay, so right, so it's let's do an example. So the idea would be you can figure out, you can calculate what the integral of f of u du is, and then just like before, whatever that antiderivative big F is, you can evaluate the top and the bottom directly, right? But in order to do that, you have to first adjust the bounds of the integration using the g function. Okay, so let's do an example here. This is a little cumbersome at first, but I think once you see it, it's very obvious why this would be the case. So let's evaluate 0 to 1 of x times x squared plus 1 to the third power dx, right? So we're going to use substitution here, u substitution. So let u equal x squared plus 1, okay? Then du is equal to 2x dx. And so that means, kind of looking up here, I've got an x dx. So that would mean that x dx is equal to du over 2. Okay, so these three here, so basically this part here and this part here is enough to get the substitution 100%. Okay, and so, but what we want to do here, what we want to pay special attention to is what to do with these bounds. So 0 to 1, we can't evaluate u at 0 and 1, but we can evaluate u, we just have to change these. So the lower limit, okay, if x is equal to 0, right, that's what the lower limit is, then u would be equal to 0 squared plus 1. So you basically want to plug in the lower limit into this, whatever your u function happens to be. Okay, so this lower limit would switch to 1. The upper limit, x is equal to 1, then u would be equal to 1 squared plus 1. Right, so again, just whatever the u function happens to be, just plug that upper limit in there and see what you get, and you get 2. Okay, so we can rewrite the integral now. 0 to 1 of x squared plus 1 cubed times x dx. Right, just kind of switch the order there. Okay, so you switch the order, and then I've got a u. So the u is x squared plus 1, so I get u cubed, and then x dx is du over 2, and then my lower bound was 0, now it's 1. My upper bound was 1, now it's 2. There we go. Right, and so now I can just take off and go right to the finish line here. And I get 1/2, and then u cubed du, the integral there would be u to the 4th over 4. And then we're going to evaluate from 1 up to 2. So I get 1/8, and then it would be 2 to the 4th minus 1 to the 4th. So 1/8, and 2 times 2 is 4, 2 is 8. So it's 16 minus 1, and so I get, what, 15 over 8. Okay, so the real kind of trick here, so this integral is like a good example of a u substitution. That's a great thing to see again, but the real kind of tricky thing here that you have to, the new thing with this example is this upper and lower limit swap. Okay, so we're swapping out what the upper and lower limit needs to be for u. And something to notice here is that you could do this calculation without changing the limits of integration. You would just have to convert your u back into x before you evaluate the integral. So let me write this down. Notice that we could have left the limits of integration alone, comma, but that would require us to evaluate them differently. Basically, would require us to convert from u back to x before doing the final evaluation. Okay, let's do an example. Let's do an example of that really quickly. So just because you don't, it's a convenience to swap those upper limits, but it's not necessary. So same integral here, x squared plus 1 to the third power times x dx. Pardon the sloppy. I started writing 3 and I meant to write a 1 there. So again, u equals x squared plus 1, du equals 2x dx, and du over 2 equals x dx. Okay, all right, so this thing here, we can plug all this jazz into it, and we get integral from, well, let's leave the bounds off for a moment. Let's plug this in. So I would get u cubed times du over 2. Okay, now one of the things that you want to be careful of here is, if you just write 0 and 1, that's actually a little misleading. So what you might want to write is x equals 0, x equals 1, right? Because the substitution has changed, right? The variables have changed to u. And so you wouldn't want to, if you left it at 0 and 1, the implication mathematically would be that you can evaluate this at 0 and 1. That would be incorrect, right? This is not equivalent to this evaluated at 0 and 1. It's equivalent, but only if you specify x equals 0, x equals 1. So, but I mean, that's not a big deal to do. You can just put that there. And then, again, you would get the same thing, u to the 4th over 4. And then it would be x equals 0 up to x equals 1. And so then before we can plug these in, we have to substitute back into the x variable, x squared plus 1 to the 4th power, and then it'd be up from 0 up to 1, like so. Right, and then of course once you convert back to x, then it's fine to just write this as 0 and 1, just so long as you know what you've done here. And so then 1/8, and you could just evaluate this directly. So 1 squared plus 1 is 2, 2 to the 4th is 16, and then 0 squared plus 1 is 1, 1 to the 4th is 1, and you get the same answer, 15 over 8. Okay. Okay, so that is the idea. All right. Let's do a couple of slightly harder examples. Well, let's do a slightly harder example to begin with here. Say we want to evaluate the integral from 1 up to 5 of x divided by the square root of 2x minus 1. Okay, so let's let u equal the square root of 2x minus 1, right? There are other things you could try first. Maybe you would say, oh, I just want to try 2x minus 1. If you try that, see where it gets you, it doesn't quite work out. This is the one you would want to choose. Like, that's the thing about integration, right? It's not like differentiation where it's like usually a direct line from beginning to end. With integrals, you have to, there's a trial and error aspect to it that is a little uncomfortable for some people. But if you try to perform this as a u substitution, letting u just be 2x minus 1, you'll come up short. Okay, so if this is our u, then this would imply that u is equal to 2x minus 1 to the 1/2. Okay, and then our du is 1/2 2x minus 1 to the negative 1/2 times 2 dx. Okay, which is equal to, I guess we should write that, du equals, the 2's cancel, and I really just get 1 over the square root of 2x minus 1. Okay, so really this is 1 over u, isn't it? Okay, so we've kind of gone around. Let's pause for a second and see what we see here. So u is equal to the square root of 2x minus 1. Okay, and I can rewrite that like this. And then du is equal to this, which is equal to 1 over the square root of 2x minus 1. So du is actually equal to 1 over u. Okay, so let's see how much of this expression we've captured here. Oh, sorry, this should also have a dx in it. Hold on. Oh, yeah, sorry. There we go. Okay. So let's see how much of this we've captured, right? So we've got this denominator is just u. Okay. Now in the top we've still got an x dx. We don't really have, we've got the dx here, and so that means that dx would be equal to u du. Okay. But what about this x? Right? We haven't captured the x yet. Right? So kind of in a previous example we saw a way to get the x would be to use the whatever expression you call u equals square root of 2x minus 1 in this case, and figure out what x needs to be in terms of u. So this is something that people will frequently do, is they'll start substituting things in just to kind of see where they're at and what's missing. Now, strictly speaking, this is kind of abusive notation, but let's just do this because I think this, a lot of times this can be helpful in kind of parsing out like what's left to grab. So I have the square root of 2x minus 1 is u, so I have x over u, and the dx is u du. All right, so I've got those pieces. So what I'm missing is this x. I need to deal with this. Okay, so what I can do is I can come back up here to this. So if u is equal to the square root of 2x minus 1, then I can square both sides, right? And I get u squared equals 2x minus 1. And so that is going to give me an expression in u for x. So that means 2x is u squared. That means 2x is u squared plus 1, and x is u squared plus 1 over 2. Okay, and so then this can be tossed in for x. And so altogether, just kind of bringing this down here, I would have 1 to 5, and I would have u down below, right? Just using the substitution here. And we know that dx is u du. So I've got that piece there. And then the x, I just found an expression for that, is u squared plus 1 over 2. Now this is ugly, right? This looks awful. But the nice thing about it is that it actually cleans up a lot. It simplifies a lot, doesn't it? The u's cancel. Right, so the u's will cancel. And I've got the 1/2. Basically, I've just got this upper piece here, don't I? I've got u squared plus 1 over 2 du. The u's cancel out, right? And then that basically makes the fraction really simple. Okay. And so we have to be careful here. This is x equals 5, x equals 1, because we haven't actually adjusted those yet. Let's do that adjustment. So the lower x equals 1, then u equals, would be the square root of 2 times 1 minus 1, which is the square root of square root of 1, which is just 1, yeah, of course. Okay, so there's the lower, and then the upper, x equals 5, so u equals 2 times 5 minus 1 square root, which equals the square root of 9, which is 3. Okay, so that means we can change this to 1 to 3 of u squared plus 1 over 2 du. Now, this is very easy to evaluate. We can get to this really quickly. You can pull the 1/2 out and do it like this. This is probably the way to go. And so you get 1/2, and then this would be u cubed over 3 plus u, and it's 1 up to 3. So we can plug all of this in, and we get 3 times 3 is 9, times 3 is 27 over 3. So 27 over 3 plus 3 minus 1/3 plus 1. Okay, and that's 1/3 times 9 plus 3 minus 1/3 minus 1. And when you do all of that, you get 16 over 3. Okay, so you can get to the end of this integral pretty quickly. Okay, now I just want to really quickly, well, actually, let's go ahead and stop the video. We'll have a part B for this video as well, simply because we're at an hour now, and I don't want the videos to be too much over an hour. So we'll be right back with part B, and we'll recap this problem and look at a few more items really quickly from this section.